Albert. This is 12th of May 2022 progress update from Mingchuan. And actually, I have presented this deep Taylor decomposition last week, but for that presentation, the explanation wasn't really clear. So this time I rearranged the whole slides, and I hope this time this is more intuitive to understand. And also, we had some questions, some problems last time, and this time I will answer that to make sure that we fully understand this deep Taylor. And this way we can have a better understanding of our heat map. So first I want to go through some intuitions. When we try to explain the decisions made by neural networks, a common approach we use would be to visualize this heat map, to highlight the pixels that have the highest contribution for that decision. And we are already very familiar with this, but in order to obtain this heat map, a common technique is called layer-wise relevance propagation. I think it's important to mention that in here because this technique is adopted by deep Taylor decomposition, and it works as shown in the graph. And you can see that we get the prediction result 0.78 for our chain, and we use this 0.78 as our relevance score, and then we redistribute this relevance to each neuron in the mid layers. And by doing this, we know exactly which neuron within the network contributes more and which contributes less. And notice that between each layer, this total relevance score 0.78 remains constant. And continue to do this, we will be able to map the relevance to the initial input, and we can construct our heat map based on that. So here is another demonstration. Assume that this image is classified as 0, and we usually interpret this output's fx, xf, as a prediction probability, but this time we think of it as a relevance score, and we back propagate this relevance score to the previous neurons. And you can notice in here the R1 and R3 correspond to the area 0 are having the higher relevance, and the neuron R2, which correspond to the area of 5, have no relevance. So this is our intuitive idea. Now the problem is we want to know how to compute this redistribution. If you look at the graph on the left, here we have Rk equals to 0.78. Again, this is the output relevance we get from the prediction result. And in the bottom, we see that we have a sum Rj. This represents the total relevance in the mid layer. And the Xj, you see from the top one, the top neuron, this Xj represents the image input or the data input in the mid layer. So in order to obtain this Rj1, which is the relevance of this specific neuron in the top, we apply simple Taylor decomposition based on the output Rk, the input Xj1, and Xj1 tilde. This Xj1 tilde is the root point that we need to select for the Taylor decomposition. In the bottom, we have the equation for that. It might not really make sense for you right now, but we will come back for this later. And going back to this graph, we can see that this whole deep Taylor decomposition is actually just the process of back propagating the relevance score from the output to the input. And this is done in a layer by layer fashion, and within each layer there are many simple Taylor decomposition to map this relevance from neurons to neurons. And one thing to keep in mind is that the relevance remains unchanged again, as I mentioned, for each layer. So therefore, the sum of the relevance for input layer is also 0.78. This means the sum of the pixel values in the heat map should be equal or proportional to the 0.78. So if, say, we have a prediction result for arching is 0, then the heat map should be completely blank. If the prediction is 1, then the heat map will either have like a lot of colored area or less colored area but with more intensity. I hope this is also intuitive. And the next one, we look into the simple Taylor decomposition. The top one equation here is the original equation for the Taylor expansion. So we use this Taylor expansion often to approximate a function like f of x at a certain point, x tilde. But in our method, this is not really what we use, because our method is called simple Taylor decomposition. So the simple Taylor decomposition is actually equivalent to the first order Taylor expansion, which is shown as the second equation here, which means we get rid of the higher terms and we only use the first term. And in the paper, it says the first order term should be just fine for heat mapping. And I think another reason they do it is to reduce the computational cost. And after we rewrite this function, we can get the function in the bottom. And this bottom function is our final equation for the simple Taylor decomposition. So notice we have this partial derivative del f over del x evaluated at the root point x tilde. So yeah, so in the previous slides and including this slides, you have been hearing about this x tilde or the root point. Now the problem is, what exactly is this root point and how do we choose this root point? So according to the papers, sorry, I forgot to make the citations, but yeah, the root point according to the papers should have two constraints. The first constraint on the top right, you can see, is that the root point x tilde should make f of x tilde equals to 0. And the second is that the x tilde should be as close as possible to x. This is not mandatory, but this is for better heat mapping. So given these two constraints, we can rearrange this function as this approximation function as the bottom left function in here, because f of x tilde will be 0, and so we get rid of that f of x tilde. And now the only thing we care about will be this partial derivative and this difference part. So this is the part I find most difficult to explain, and also Professor Clement and Professor Deepu were a bit confused by it. But the overall idea is that if we find a root point x tilde such that f of x tilde equals to 0, that means, like, if we think of this function f as a classification function, and it outputs 0 means no object of interest is detected. It outputs 1 means that the object of interest is detected and the probability is 100%. The f of x tilde equals to 0 basically means that this function does not detect the object of interest. So look at the demonstration here in the right bottom. The input image is x, and we find the root point x tilde. So in here we just blurred the image. And now when the image is blurred, the f of x tilde equals to 0. And that way, we can get the difference. So the difference will be this building only. Imagine if we find if we have a like a random root point, we cannot get the difference, right? We cannot get the difference as the only like object of interest. We can get something else. We can get some random difference. But this time, if we find the good root point, we can get a good difference. And this gradient basically means the sensitivity of this object building to each pixel. And combine that using pixel-wise multiplication, we can get a heat map. If you have questions, you can always ask me about this. Maybe I can explain in further details, but yeah, I will continue for now. Now the problem is, given an input image x, how do we choose a root point to satisfy these two conditions? Again, the first condition is this x tilde should make f of x tilde equals to 0, and second, this x tilde should be as close as possible to x. So we make a simplified assumption that this input space, this image space, is only two-dimensional. Usually, our input image space is like have very high dimensions, but we only do this for like a simplicity demonstration purpose. And there exists a line, and every point on this line will have the function f to output 0. So that means every point on this line will satisfy our first condition. And now we just need to find a direction from x to this line, and their intercept would be our root point. So actually any point on this line can be our root point again, but the reason we go from x is because we want to search for a closest point. And of course, the best way we can think of is to find a perpendicular line. So here comes the W square rule, and this rule choose the root point x tilde that is nearest to the input x using a perpendicular line. And now if we go back to the relevance redistribution process, remember I said like we could go back to this. I'll come back to visit this simple Taylor decomposition function later. So if we choose a root point using W square rule, we can rewrite this function in a new way. So in this new equation, we only need the weight and the relevance of Rk to redistribute the relevance to Rj1. And this equation will be our final propagation equation between each neuron in the mid layer. However, there's a potential problem. The problem of this W square rule is that the root point that is perpendicular to x may fall out of the image space. It may turn out to have like a negative value, but for images we cannot have we can only have positive values. So this root point will be invalid. And alternatively, here we have the z rule. So the z rule connects the input point x to the 0 vector and choose the intercept to be the root point. And by doing this, we can guarantee that we can find a root point, a valid root point, although this root point may not be closest to x. So again, by finding this root point by the z rule, we will be able to rearrange the relevance function. So this time, in addition to the weight vector, we also utilize the input data xj1, and this equation will be our final propagation equation. And in case we have an output equal to 0, say there's absolutely no arching detected by our model, these two equations can also work well, because if rk equals to 0, then the rj1 will equal to 0, and all rj will be equal to 0 as well. And there will be no relevance propagated to the previous layers, and therefore we have a blank heat map. So in comparison, both rules have their pros and their cons, and I think Prita selected the Z rule, which I think is also a common selection, and there's no problem about that, except that the root point x tilde may not always be optimal. This solution may not be optimal, but I think this have little influence to our heat map. And there are also a couple more rules discussed in the paper, but they are all very similar in principle, and they all have their pros and cons. So I don't think there's a problem if we choose Z rule for our explainable model. And now if we come back to this overview, I hope now we have a clear picture of what's happening behind. Again, just backpropagating this relevance to each neuron, and then we map it to the input neurons, and then using the input neurons, we can reconstruct this visualization heat map. So here's the final takeaway. This is what I have learned while I was exploring this technique. So deep tailor has been a widely used method since it has been published in 2017. And there are over 900 citations, and a lot of applications use this technique to explain their model. So I think it kind of builds on the layer-wise relevance propagation and simple Taylor expansion, which are even more cited and tested. And this builds up the credibility of this method. I think the credibility is very important. Like, imagine if we cannot trust our neural network itself and we still have to use it, we have to at least make sure that the way we explain this network is recognized and accepted by other people in the industry. Like, for example, like for me, I cannot just come up with my own explainable technique and tell people to use it in the industry. Even if my technique is published and peer-reviewed, I still cannot do that. Like, people will come up and say it's not trustworthy because I've never seen someone explaining a network like this. So my point is, my overall takeaway is, in aerospace engineering and manufacturing, I think that the explainable technique we choose has to be widely used, widely tested, and widely recognized. And for the next steps, I have discussed with Professor Deepu, and I think I will be look into some details, like some further details about this deep Taylor decomposition, and maybe I could review some problems of this technique and see if there's any alternative method for this. And also, Prita has sent me some papers like pointing out these problems of deep Taylor and their solution for that. So maybe from this I can do some further exploration and see what we can do to improve our explainable model. Yeah, that's it. Thank you.